Hi and welcome back. Today we're going to be looking at the second of our spectroscopic techniques that we use to help inform us what molecules we have in organic chemistry. So let's get started. Today it will be infrared spectroscopy. Essentially, as we've mentioned before, spectroscopy is the way in which we can help identify chemical compounds. On the whole, it allows us to identify compounds by the way in which they react with light, or more specifically, energy from the electromagnetic spectrum. Different parts of the molecule will interact with different parts of the electromagnetic spectrum, and we've seen this previously in Year 11 where we looked at flame colors and how this was used in AAS spectroscopy to determine the concentration of metal ions using atomic absorption spectroscopy. So these transitions happen within the visible spectrum of the electromagnetic spectrum, giving us different colors of light dependent on the energy. And you may remember that if we have Roy Jabiv, then this is low energy at the red going up to high energy in the violet. We're going to be looking now at what happens to molecules in different regions of this spectrum, and in this video we're going to be looking at infrared, which sits just below the visible energy spectrum in terms of energy. So molecules can absorb energy and cause a variety of changes to occur, and we need to be able to specify what changes are occurring in the molecule to answer questions in regards to these topics. So as I mentioned before, electron transitions going from ground state to excited state gives us spectra within the visible region. But these changes can depend on two things: the nature of the substance or the molecule and the amount of electromagnetic energy involved. Is it a high energy or a low energy transition? Energy changes can be categorized, and these are kinetic energy. So these are associated with translation, essentially the molecule moving around from one position and another in space. The energy of the rotation of the molecule as a whole, so specific bonds in the molecule, the vibration of the covalent bonds within the molecule, and the potential energy of the electrons and the energy transitions. So a molecule can basically undergo electronic energy transitions, vibrational energy, rotational energy, and translational energy. When we're talking about infrared spectroscopy, we are talking about changes in the vibrational modes of bonds within a molecule predominantly. So infrared radiation is lower in energy and a longer wavelength than visible and ultraviolet light. So if we look at our spectrum here, we can see that as we move from left to right, we get smaller wavelengths, higher energy. So we're in this range here with the infrared being here. And this infrared radiation is not enough to promote electron transitions. So we're not talking about the excitation of electrons as we were with flame colors and AAS, but it is enough to cause changes in the bond movements within molecules. And it's important when we talk about what causes the peaks in these spectra that it is changes in the vibrational modes. So we have a number of vibrational modes or energy levels within molecules. Essentially, this treats bonds like two atoms being joined by a spring. And if you do physics, then you know about Hooke's law. But essentially, what we're looking at here is that IR radiation being lower energy than visible light, they have a longer wavelength and lower frequency. It's not energetic enough to promote electrons, but it can cause changes in the covalent bonds. It utilizes the fact that the covalent bonds bend and stretch, occupying discrete vibrational energy levels. That being, if the bonding is different, we get different vibrations, and these different vibrations have different energy transitions between high and low energy. As the atoms in the bonds change position due to bonding and stretching, the molecule vibrates, and that is what we can detect. So molecules are only able to occupy discrete vibrational energy levels. So it will absorb a discrete or specific amount of energy to move from one vibrational energy level to the next. So from a low energy to a high energy state and back. So we can work out from the infrared spectrum the types of vibrations that occur and therefore the types of bonds that are present. So we can figure out if it's a single bond between a carbon and an oxygen or a carbon and a hydrogen. We can even determine if it's a double bond between a carbon and an oxygen by measuring these discrete energy levels and the changes that we see. So as you can see from this diagram here, there are multiple ways in which atoms that are bonded can move. They can stretch, they can scissor. We don't need to know the specific vibrational modes that molecules can undergo. We need to know, however, that these vibrational modes give changes in energy within the molecule and that they can be detected by this technique known as infrared spectroscopy. The energy absorption that we see is linked to bond strength. So the frequency of the energy absorbed is dependent on the strength of the bond and the mass of the atoms attached. A single bond will absorb lower energy than a triple bond. It will take more energy to get it moving, is essentially what this is saying. Bonds that involve heavy atoms absorb lower energy. So if you have a heavy thing on a spring, it takes less energy to get it started bouncing than something that is light. So we will see higher energy and therefore higher wave number absorbances for bonds that increase in strength. The bond energy therefore is proportional to the infrared absorption stretch that we see, and these absorption stretches are listed in your data book. You don't need to memorize them. The energy of the absorption also depends on the lightness of the atom. So here we can see here that high energy 3000 for the small, less weighty hydrogen, whereas we see a absorbance at around 600 for the heavy bromine atom being attached to the carbon. This is what a typical spectrum will look like. The signal is generated and measured in transmittance. We always know an IR spectrum by the fact that the peaks seem to fall from the top, sort of like stalactites in a cave. It's the inverse of absorbance because we are seeing transmittance of energy. So the spectrum appears upside down. The colors here show ranges of bands where we find different types of bonds, and you can see that the double bonds, C double bond O, C double bond C, all appear in this range here. And then one area we will particularly be interested in is this 3000 to 3500, as this is where we will find OH stretches for carboxylic acids and alcohols. Typically, at below 1500, unless a peak is labeled, we're not going to pay too much attention to it. This is known as the fingerprint region. All molecules will have a very complex absorption spectrum or transmittance spectrum in this area. So, like with mass spectrometry, all molecules will give a unique particular pattern in the infrared. We can use computer databases to exactly overlay these. However, our eyes can't see that level of detail. So we will be looking for particular characteristic features when we come to interpreting these spectra. So when we interpret the data, it's useful to divide the spectrum into the region. So our fingerprint region, the areas where we expect to see double bonds, triple bonds, and then our single bond absorptions that we're interested in, such as the NH for the amines, OH for carboxylic acids and alcohols, and CHs for pretty much all our hydrocarbons. IR tends to be used qualitatively to determine the type of bonds or functional groups present in a compound, and it can be more useful for specific compounds than others, i.e. it will be challenging to find the difference between pentane and hexane in an IR because it will have CC and CH bonds. All those bonds will be of a similar energy, so it will be hard for us to see any difference in the spectrum. However, if we were trying to compare an alkanol and a carboxylic acid, there would be characteristic differences that would allow us to determine these two molecules apart in the IR spectrum. Most functional groups have characteristic absorption bands, so we can determine if there is a CC present by looking for a peak between 1640 and 1680, or an OH at 3400 to 3650 would be characteristic of an alcohol. The fingerprint region, as I mentioned before, has a large number of absorptions. This is characteristic, like a fingerprint per molecule, so it can be used to help detect molecules, but we don't get much information from it. The characteristic absorption bands are listed in your data booklet, and these are the key ones that we will look for when using for interpretation. Things like the CCL, you'll notice this is in the fingerprint region and will usually be labeled if it is expected for you to be able to see this or pay attention to it. C double bond O, which we would see if we were looking at aldehydes, carboxylic acids, ketones, can be very useful for helping us to characterize a molecule. OH acids at 2500 to 3300, and OH alcohols, which are a little bit higher at 3200 to 3550. This is the key ones, the ones that are listed in the data booklet. You don't need to memorize them. They just expect you to be able to apply this knowledge. The intensity of the band can also be characteristic. You can see here that this is labeled as a strong absorbance, medium and weak, so how far it comes down from the top towards the bottom of the plot, and then broad versus narrow. These are guidelines only, but they help us to be able to recognize the patterns as we put the pieces of the puzzle together. So, couple of key things to remember as we sum up for IR. The energy of the radiation absorbed and released depends on the types of bonds in the molecule, the environment or other bonds in the molecule, and the wavelength absorbed depends on the entire molecular structure. It is important to remember that it is changes in vibrational modes that come about as we go from a low energy to high energy vibration of the modes of the bonds within molecules. Okay, so we're seeing transitions in the vibrational modes of the bonds when we look at infrared spectroscopy. Next up, we will be looking at interpreting of spectra, and we'll go through looking at some of these characteristic peaks and what information we get from them.